Previously, we discussed how to evaluate real trig integrals with Cauchy's residue theorem. This is a continuation of that previous video, so I'll strongly suggest you go watch that, because you may be lost if you did not see that. But anyways, this is Complex Analysis by a Physicist, and let's continue discussing how to evaluate real trig integrals with Cauchy's residue theorem. Okay, so last time we went over how to evaluate Cauchy's residue theorem, and we used this sort of idea here that for integrals on bounds 0 to 2 pi that were functions of sine and cosine, we could convert those to complex integrals using the following conversions for cosine, sine, and d theta, and integrate about a simple closed contour, otherwise just mod z equals 1, or the unit circle in the complex plane. And we saw that we could evaluate this integral here, 1 divided by 2 plus sine theta on bound 0 to 2 pi equals 2 pi per root 3 by Cauchy's residue theorem. And that's really useful to be able to evaluate these kinds of integrals. But I didn't really give you the full picture, okay? Because what we can do here is, let's say that we want to evaluate an integral on bounds 0 to pi, or let's say 0 to pi halves or whatnot. We can take advantage of the geometry of our situation and convert that to an integral on bounds 0 to 2 pi so that we can evaluate that integral with Cauchy's residue theorem. And then we can just toss a factor of, at least in this case, 1/2 in front. If this was pi halves, it'd be 1/4 and so on and so forth. And so we can really take advantage of geometry really nicely and really well here. And, like I said, standard conversions stay the same, and so we're just tossing a factor of 1/2 in front. And so let's use this idea, or let's use this principle to evaluate an integral on bounds other than 0 to 2 pi. So here is the integral that we're going to try to evaluate, and you may notice, actually, if we go back to the other blackboard, that it looks very similar to this integral here from before, but instead we're just changing this sign to a cosine, and we're changing our bounds from 0 to 2 pi just to 0 to pi. All right, so let's do our conversion here, and let's convert this to an integral that we can evaluate. So this is just going to be 1/2 integral 0 to 2 pi 1 divided by 2 plus cosine theta d theta. And then now this is in a form that we can actually use Cauchy's residue theorem for. So let's do that, and let's apply our conversion here. So this is going to equal 1/2 times the integral. And I'm going to write mod z equals 1 here just once. Otherwise, I'll just write it as c, being a simple closed contour. Of 1 divided by 2 plus z inverse divided by 2 dz per I z. And now comes the algebra that I didn't want to do last time, that we're gonna keep doing here. So all right, now let's distribute the iz through. So you're going to get a 1/2 integral over a closed contour. 1 divided by 2iz plus iz squared per 2 plus I per 2 dz. And then we'll move over to the next whiteboard. So we'll just dot this. And then dot to continue it. So from before, you can see that there's very clearly a multiple of 2 here. So we're going to multiply this entire thing by 2 all the way through, and that'll cancel out our 1/2 term in front. So we're going to just end up getting an integral over our contour of 1 divided by 4iz plus z squared plus I or I'm sorry, iz squared. Forgot the extra term of I in there. And then still dz. Can't forget that. All right, now we can factor out an I term. So here we go. We're going to get a 1 on I integral over our contour. 1 divided by 4. Actually, we can simplify this easier to a z squared plus 4z plus 1 dz. All right. And now this is something that we can evaluate with Cauchy's residue theorem. So let's try and examine some roots here. You could do quadratic formula here to get your roots. I'll actually do them out this time. In the last video I didn't do that. So for the roots, with quadratic formula we'll get a -4 plus or minus the square root of 16 minus 4, which is just going to end up being 12 divided by 2. And so we'll end up getting roots of -2 plus or minus root 3. And now we need to examine which one of these roots, or if both of these roots are in our contour. Remember, our contour is just mod z equals 1, which all of this is just a side work. So let me just write something there to sort of divvy this up. Anyways, I think it's pretty clear to see actually here that -2 minus root 3 is going to obviously be bigger than, or the absolute value is going to be bigger than 1. Meanwhile, -2 plus root 3 will be inside 1. So we're only going to have that one root. So let's just carry this on to the next blackboard. Okay, and so now we can evaluate this with Cauchy's residue theorem. So we have that 1 on I. Can't forget about that. Times 2 pi I times the residue as z equals -2 plus root 3 of 1 divided by z squared plus 4z plus 1. Okay, and this is a pole, so we can factor this out and we can use the limit rule. So I'll combine that into just one step. So our i's are going to cancel, so we're just going to get a 2 pi times the limit as z tends towards -2 plus root 3. And then we're going to have z plus 2 minus root 3 divided by z plus 2 minus root 3 times z plus 2 plus root 3. And you can see these terms cancel out. Then we're just going to take z or take our limit here and evaluate this limit. So when we do that, we end up getting a 2 pi I. I'm sorry, not the I. I'm so used to having the I there from Cauchy's residue theorem. 2 pi I. I'm sorry, I just said it again. So we're going to have 2 pi divided by 2 root 3 in the denominator. Our 2's are going to cancel, so you're going to get a pi per root 3, which actually looks a little bit interesting, okay? Remember, we had that term, we had that factor of 1/2, so this is going to equal our integral 0 to pi 1 divide 2 plus cosine of theta d theta, which this is our final solution. But remember, we're on 0 to 2 pi, so we have an extra factor of 1/2. If this was on bounds 0 to pi, let me just rewrite this out. If we're on bounds 0 to 2 pi, 1 divide 2 plus cosine theta d theta. Well, if we evaluate one of these integrals, let's say on bounds 0 to pi or 0 to 2 pi, we can easily convert them. So we had that factor of 1/2 out here before, so to evaluate this integral, knowing that solution, we can just multiply by 2 to get 2 pi per root 3. And if we go back a ways, or if you go back to the previous video, you'll see that we got the same solution for this integral right here with Cauchy's residue theorem. Now, did we evaluate this incorrectly? Well, no. If you go to your favorite integral calculator, it will it'll give you the same result. And actually, this is a peculiar integral, one that I actually specifically chose for this reason, because these integrals are equivalent. So we can say that this also equals the integral on bounds 0 to 2 pi of 1 divided by 2 plus sine theta d theta. It's kind of interesting to really think about, but that's just kind of an aside. That is how you evaluate real trig integrals, though, with Cauchy's residue theorem, and I'm happy that I was able to get this second example out, because it is a little bit interesting to see that both of these are the same. But once you really get in the mindset or in the groove of how to evaluate these integrals, they come across pretty straightforwardly. So that's really it. If you have any questions, let me know, and thank you very much for watching. Hope to see you again next time.